about when we think about the sensors themselves. So I want to remind you that in this course, when I call sensor, is everything that is detects light. So it could be eyes, it could be cameras, it could be detectors in single point confocals. I'm not going to talk about eyes right now. I'm going to talk about the other two. So what is a good sensor? We think about the way the emitted light manages to make its way through the objective, through the emission filter, if there is one, etc., through the grids. It makes its way to the sensor. And we have a number of photons that come in. So let's say we have 3 photons coming into the sensor. And if only 1 photon is detected, that is because not all the photons can be detected. So we will talk about that. And this is the process of building an image. So first we get some photons are detected, and they are then they trigger inside the machine, inside the sensor, they trigger an electron. So we get an electron. And then afterwards, the electrons are amplified. So normally we should get 1 photon, gives 1 electron, then there's a level of amplification, several rounds of amplification sometimes, and then we end up with lots of electrons. And then, so that is a current basically, and then we read the voltage. And this voltage is an analog signal. So it's a continuous signal with an infinity of possible values. And we clearly need to make it digital. And so we have something called a conversion to a digital signal in the analog to digital converter. And then we get finally an image. So the number of the voltage is being read, it's being converted to a digital signal, which gives us an integer, and with a number of possible, so finite number of possible values. And this is 1 pixel. And this happens for all the pixels, either sequentially in a single point confocal or altogether in camera-based systems. So what can go wrong or right, and what do we want in this process? So this is true for cameras and detectors. The number one thing that we want is we would like the sensor to efficiently detect the photons, the incoming photons. So if we have 3 photons here, we'd like ideally we would like the sensor to detect 3 photons here. We would also like to have an efficient electron amplification in here in this process. And in the process of amplifying and reading and everything, we would like no noise to be created. So low noise creation. And we want all this to happen at super fast speed. This is a good sensor. And in all this, we also want high resolution and high dynamic range. So you know about the high resolution. It's basically the digital resolution that we just spoke about. And what we want is to have small pixels if possible, but we still want a high dynamic range, and this we will speak about a bit later. So the dynamic range, the resolution, and the efficiency of detecting the photons depend on the specifications of the camera or of the sensor. So basically, when you buy a sensor, you need to be careful about these things, because once you have bought the thing, you cannot change them. It comes with the machine, basically. So we can't do anything about this. However, the other things like dynamic range partly, and then also the efficiency of amplification, the noise and the speed, these are in the settings, and therefore we can influence this when we're sitting by the microscope. So in this lecture, we're going to, or the next lecture, we're going to talk about the all these efficiency of detection and also the speed in here. So the sensitivity of the sensor is basically how many incoming photons are detected. So it's called the quantum efficiency. So if I have 3 photons coming in and I only detect 1, it's not very good. And I would like to have a little bit more. So the quantum efficiency is the percentage of incoming photon that trigger a signal. So in here, it would be 33%. Okay. And of course, it's not always the case, so it changes a little bit, but pretty much it's going to be this percentage of efficiency. It's just like a statistical process, basically. So the quantum efficiency is the percentage of photons, incoming photons that trigger a signal in the sensor. And the sensitivity of the sensor depends, it differs across the spectrum. So for example, and also for different of different machines. So the maximum, the peak quantum efficiency, I will show you afterwards what happens in the spectrum, of a detector in a single point confocal, if it's a conventional PMT. I've told you at the beginning that detectors, they're different types, and cameras, they're also different types. So one type is a conventional PMT, and which means photomultiplier tube. These have a quantum efficiency of 35%. So 2/3 of the incoming photons that we have worked so hard in sending to the sensor are anyway not detected. And then if the detector is a GASP detector, then it's a bit higher, it's about 45%. Anyway, more than half of the photons are lost. With cameras, we have different types of cameras, but basically we are in the best types of camera, the back illuminated CMOS wavelengths, you see these were 95% quantum efficiency, which means that at the peak, we detect almost all the incoming photons. Now I say at the peak because it's different across the spectrum. So you can see here the spectrum of light that we are actually imaging. So these would be the photons that we're sending to the sensor. And here is the quantum efficiency, and you can see that for a gas detector, so this is only for detectors. For a gas detector, you can see that we reach about 45%. So this is what I wrote here. This is at the highest peak, and it's conveniently within the range that we want. But you see that when we're imaging green, we're at the highest for almost everything. But if we are imaging at 650, 700 or something, we already have a lower quantum efficiency when we image. So this influences our imaging quite a lot because we do not want to put a dim. So if we have a fluorophore that you know is going to be dim, either the fluorophore is dim or we have a little abundance of this protein, we want to try and avoid having imaging in that area where we have a lower quantum efficiency of the sensor. So this was for detectors. And you can see in here that, for example, at 800 nanometers, we have 0. And in this gas detector, we have 20%. So it's a special gas detector, which is extended in the near infrared, and we have only 20%. So 80% of the photons are lost, not detected. Now, this is for an SCMOS camera. And what you can see here between the front illuminated, the back illuminated, you don't need to bother with what it is, basically two different types of cameras. And we can see that the back illuminated SCMOS cameras, they have a peak quantum efficiency of 95%, but it's not even across the spectrum again. So at around 400 something, you see that we are about 70+%. And if we go on the other side of the spectrum, we also have a lower quantum efficiency. So at 800 nanometers, we have about 60% quantum efficiency, but it's anyway better than the detectors. And the reason why I point 800 nanometers is because there's a very strong development in the near infrared for the fluorophores. So the tendency is very much to go into the near infrared, because if we would go to the shorter wavelengths, they are very aggressive for the sample. So the longer wavelengths have a bit less resolution, but they are anyway very gentle, and they're also more penetrant. So there's a lot of development in in the near infrared, and it's more and more common that microscopes have the capability to excite fluorophores around 700 something. And so then you have to look a little bit at where you emit and see that your sensor has a proper quantum efficiency in that range. So this is another type of camera, EMCCDs, and we can see that at 800, we have a very high quantum efficiency of 80%. So there's a big difference in the quantum efficiencies between different sensors and depending on where we look in the spectrum. So most of the sensors that we're using are black and white sensors, and that's because they are more sensitive than color sensors. But if you image colored dyes, for example, H&E stains or DAB, then you need to have a color camera so that you can see the colors. You will not see it because it doesn't fluoresce. You will not see it with black and white. You will see something, but you will not know which color you're looking at. So when you use a color camera, we have a special filter on top of the camera chip. So these are all the camera pixels. And these filters have a color, and they're organized like this, so that within a block, let's say we have 2 green, 1 red, and 1 blue. And this is meant to represent the human eye. So it's designed to match the human eye, where I was telling you that our eyes are very sensitive in the green and less sensitive in the red and the blue, and everything else is, we cannot see them at all. So this is the reason why there's twice the number of green compared to red and blue. So this is called a biofilter, and this has blue, red, and green, and red. But the pixels in general are very small, but really in reality, we have 4 pixels giving 1 pixel, because to have a color, 1 pixel in the image that gives us a color, then we need to put all together these 4 pixels. So even though you go to the camera specifications, if your camera is a color camera, you go to the camera specifications, you might find that it has very, very tiny pixels. You think, oh, great, my camera has a fantastic digital resolution, but actually you need to multiply by 4 to know the real size in the image. And when it comes to quantum efficiency, we also have quite a high quantum efficiency in this camera. It is quite reasonable, let's say, and it also varies with the wavelength. So this is a little bit what it's about in this lecture. I'm going to talk a little bit about speed now, and then afterwards in the next lecture, we're going to talk a lot about the noise and also the background. So speed, for detectors, we are on a single point confocal, right? So we scan pixel by pixel, and then the scanner stays for a certain time on each pixel, and this is called the pixel dwell time. So it's basically the number of microseconds per pixel where the scanner stays before it jumps to the next point. And you can influence this on your single point confocal by changing the scan speed. If you change the scan speed, it's going to change the pixel dwell time, so the amount of microseconds that your scanner stays. And of course, if you go to a slow scan speed, it's going to take much longer to image, and you're going to bleach more, and you have a higher risk of sending the fluorophores to the dark state than if you scan faster. So if you have an image if you acquire an image on a single point confocal with a 2048 by 2048 pixels, which is something you can choose, so you get over 4 million pixels in the image, the pixel dwell time can be 4 microns, so more microseconds per pixel. So this type of numbers, they do change a little bit between the microscope, not much, but they do change a little bit. And so you could have a pixel dwell time of 4 microseconds, and this is per pixel. And so if we image all these 4 million pixels, and with 4 microseconds, then we end up with 17 seconds per image, okay? If now we choose to use the bidirectional scan, so it is possible, and on all microscopes, single point confocal, you have the possibility to scan in 2 directions if you want, then you will pretty much divide the scan speed by 2. And so you will get, you will go much faster. And then I also see here, it means how many images, 1/10 of an image per second, because this is the way I will compare with the other systems. If you have a resonance scanner, you can go much faster, but you will have maybe more noise. So it depends also on the resonance scanner. So we will have a look as well. The advantage is that you can at least image several colors at the same time, because you always have more than one sensor on a single point confocal. So at least we can parallelize a few things if we do not have any bleed through. So when it comes to cameras, all the pixels are exposed at the same time. The camera pixels are all exposed at the same time. And we can get, it's very common that we acquire images at 10 milliseconds for the whole image. So this, if we acquire with 2048 by 2048 pixels, some cameras have even more pixels. So that's again 4 million pixels. We're talking about going at 100 images per second. So we were here with the same number of pixels, we were here at 0.1 image per second, and now we are 1,000 times faster. So yes, cameras are faster. There is something called the readout rate in a camera, where that you can change. So in general, it's written in megahertz. And that means how fast the electrons are removed from the chip before the next image is acquired. And we will talk about the consequences of this. But this is something that you can influence if you want to go faster. Depending on the readout rate, you can change the speed of the acquisition. So unfortunately, if you use a high readout rate, like if you use the 540, then you get a readout noise. And this we will talk about later today, the noise. And with the camera, we can only image one color at a time, except if we have several cameras or some tricks with a single camera. But most of you who have a camera, you can image only one color at a time. So you can see that with the same number of pixels, we have a much higher frame rate, as it's called. So the speed is much higher with a camera. But here we can compensate a tiny bit by having several colors at once. And here we have only one color at a time. So camera-based systems are much faster. And if you want to go fast in a single point confocal, use the bidirectional scanning. It's always there in the area where you can put, for example, the number of pixels, or you can change the scan area. It's somewhere there. You will have monodirectional, bidirectional. Sometimes it is shown as like an arrow in one direction and then another arrow in the other direction, so that you can image one way or the other. And that will allow you to go faster on single point confocals. And on camera-based systems, if you increase the readout rate, you will go faster. But unfortunately, it increases the noise. So we will see this in the speed workshop. And now I'm going to stop this and ask you if you have any questions about this.